Okay, hello everyone in a new video. So we have reached part 7 of chapter 10, which is the Archimedes upthrust and the third unit of mechanics, and this is the final part. In this part we are going to complete solving exercises on this chapter. So exercise number 15. Consider a solid S of density rho S is equal to 1 gram per centimeter cube. So knowing that a gram per centimeter cube is not a unit of density, in order to convert from a gram per centimeter cube to kilogram per meter cube, we simply multiply by 1000. Then 1 multiplied by 1000. Then the density of the solid in the SI is given by 1000 kilogram per meter cube. So this is the density of the solid S. S is immersed in a liquid of density rho. So the liquid is of density rho. S is in equilibrium. So at any moment in this exercise we can use the condition of equilibrium, and the volume of the immersed part is VI, adjacent document. So they mentioned this document, then now we can use it. So notice that here the solid S is floating at the surface of the liquid, and this is the volume of the emergent part. Now number 1, S floats on the surface of a liquid. So 1.1. Name the two forces acting on S. So here, because the solid S has a density, or in other words it has a mass, then it will be directly subjected to the weight which acts on the center of gravity vertically downward like this. So one of the forces is given by the weight W, and here it's important that we distinguish between two types of weights, the real weight and the apparent weight. But whenever we are considering forces, we are always interested in the real weight and not the apparent weight. And the other force, so they are telling me that there are two forces, so one of them is the weight, and here because we have a liquid, then the solid S will be directly subjected to the Archimedes upthrust force F. So the Archimedes upthrust denoted by F upthrust. So these are the two forces. Now in 1.2, tell for each of the two forces whether it's a contact force or an action from a distance force. So knowing that the action at a distance force are given only by the three forces, the weight, the electric, and the magnetic, therefore the weight W is classified as an action from a distance, and all other forces are classified as contact forces, and in particular the Archimedes upthrust, F upthrust. So this is a contact force. Now in 1.3, give the line of action and the direction of each of these two forces. Then let's start by the weight W. So we are only interested in the line of action and the direction corresponding to the pendulum. So we will list them in this order, starting with the line of action. We know that always the weight acts vertically downward, so the line of action is vertical, whereas the direction is given by downward. And now as for the Archimedes upthrust, so we know that the Archimedes upthrust always opposes the action of the weight, so the line of action is vertical and the direction is upward. Then the line of action is given by vertical, and the direction is upward. Now in 1.4, write down the vector relation between these two forces, and here by the relation they mean the equality, or in other words the condition of equilibrium. Here we can use the condition of equilibrium because they already mentioned in the exercise that S is in equilibrium. So let's write as a title at equilibrium. Then how do we apply this condition? Always on the left we write the sum of forces acting on the solid S, and they are given by the weight and F upthrust. So W vector plus F upthrust. And on the other side of this equation we write the zero vector. We don't forget the vectors on any of these quantities, and in particular the zero. So the zero vector corresponding for the condition of equilibrium. Now moving F upthrust to the right hand side, we have that W vector is equal to minus F upthrust. So what does the first equation tells us? That the effect of both forces acting on the solid S cancel each other to give us the condition of equilibrium. Whereas the second equation tells us that both forces have the same line of action, the minus sign for the opposite direction, and same magnitude. So this is the condition of equilibrium, or the vector relation. Now in 1.5, reproduce the figure and represent without a scale these two forces. So they are telling me represent. In other words, we need to draw the forces acting on the solid S without a scale. So let's first reproduce the figure. So let's suppose this is the container. And this is the liquid. And this is the solid S. Now let's start by representing the weight. So the weight acts on the solid S vertically downward, and the point of application, because it's classified as an action at a distance, action from a distance, then the point of application will be the center of gravity G of the solid S. So this is the center of gravity G. So let's consider that the length of this vector, which is W, is given by two divisions. So here, why W is given by two divisions? For example, we can draw the vector W to be given by three divisions, and this is because they are telling me represent without scale. And now let's represent the other force, which is given by F upthrust. So in order to represent the other force F upthrust, we need first to determine or locate the point of application of the force. And the point of application is given by the center of gravity of the immersed part. So this is the immersed part, and its center of gravity will be the point here. So let's name this point to be the point A. I have moved the point A a bit to the right in order for the drawing to be clear. Now, so F upthrust acts vertically upward. So what's the length of F upthrust? Although here we are representing the forces without scale, but since I've considered the length of the vector W to be two divisions, so it's important that we must represent F upthrust by two divisions as well, because according to this equation, they have the same magnitude. So let's suppose that this is two division like this. So this is it for part 1.5. Number 2, we repeat the experiment by putting S successively in different liquids. So here what we are doing is that this is the liquid. So we are repeating this experiment by changing each time the liquid. So for example, we are changing the liquid from oil to water to alcohol, etc. So the adjacent graph, they mentioned this graph, now we can use it, represents the variation of Vi as function of rho. So here the y-axis is labeled by the quantity Vi, which represents the immersed part given in centimeter cube, whereas the x-axis is labeled by the density rho. What does rho represent? It represents the density of the liquid, having the unit gram per centimeter cube. Now let me make some space. So we are in number 2.1. According to the graph, does the volume of the immersed part increase or decrease when the density of the liquid increases? So first, we need to identify how one should read the graph. So they are telling me as when the density of the liquid increases. So this is the density rho, and the values of rho are given by 1, for example here 2, 3, 4 and 5. So this is the increasing value of rho, so we must read the graph like this. As rho increases, so this is the curve that relates the value of rho to Vi. We can notice that Vi decreases as rho increases, because these are the values of Vi. So here it's 200, here it's 100, and here it is given by 25. Then let's say as rho increases, the volume of the immersed part, Vi, decreases. Now in 2.2, for rho is equal to 1 gram per centimeter cube as is totally immersed in the liquid, Y. So here, for rho is equal to 1 gram per centimeter cube, recall that what does rho represent? It represents the density of the liquid. So Y as is totally immersed in the liquid in this case. So knowing that rho is equal to 1 gram per centimeter cube, and the density of the solid is given by also 1 gram per centimeter cube. Now comparing the two densities, we can see that rho in this case is equal to rho S. So what does it mean when rho is equal to rho S? So the density of the solid is equal to the density of the liquid, which means that the solid S will float inside the liquid. So in this case, the solid S will float inside the liquid like this. So let's say since the density of the solid is equal to the density of the liquid, which means that S floats inside the liquid, then because it's floating inside the liquid, which means that S is completely immersed in the liquid, then S is completely immersed in the liquid. Now finally in part 2.3, deduce graphically the volume of S, and by deduce it means that we need to use the previous part. And they are telling me graphically, so we must use the graph. So here let's write as a title graphically. So recall that they usually give half a mark for this statement. So referring to the graph, knowing that we need to use the previous part, which is part 2.2, in which the density is given by 1 gram per centimeter cube corresponding to this volume. So this value corresponds to this point on the curve, having a value of the immersed part given by Vi is equal to 200 centimeter cube. Then for rho is equal to 1 gram per centimeter cube, we have that the volume of the immersed part is equal to 200 centimeter cube. So the volume Vi is given by 200 centimeter cube. So, but they are telling me to deduce graphically the volume of S. Now here from the graph, knowing the value of rho, we have determined the volume Vi. So, but what does Vi represent? It represents the volume of the immersed part. But knowing that when the density is given by 1 gram per centimeter cube, S is totally immersed in the liquid. So let's say since S is totally immersed in the liquid, and this is because the density rho is given by 1 gram per centimeter cube, then the volume V of the solid is equal to the immersed volume, which is equal to 200 centimeter cube. So V is equal to 200 centimeter cube. Moreover, knowing that centimeter cube is not the SI unit of volume, in order to convert from centimeter cube to meter cube, you multiply by 10 to the power minus 6. Then 200 multiplied by 10 to the power minus 6. Plugging this on the calculator, then the volume V is given by 2 times 10 to the power minus 4 meter cube. So the volume of the solid S is given by 2 times 10 to the power minus 4 meter cube. So this is it for this exercise. Now exercise number 16, the aim of this exercise is to determine the magnitude of the force exerted by the bottom of a container containing water on a sphere S totally immersed in water. So this is important. Now at the end of the exercise, I will explain what's meant by the force exerted by the bottom of the container containing water. So the mass of S is M is equal to 0.5 kilograms. And its total volume V is given by 2 times 10 to the power minus 4 meter cube. Given the density of water to be rho is equal to 1000 kilogram per meter cube, and the gravitational field strength is given by 10 Newton per kilogram, which means that we are performing this experiment on the surface of the Earth. Real weight of S, part 1, 1.1, calculate the magnitude of the weight W vector of S. So here because we have a liquid, we must distinguish between two types of weights, the real weight and the apparent. And because we are interested in the vectors, so for this reason this weight represents the real weight. And moreover, as a title, the title is given by the real weight. Then we are in 1.1, the magnitude is given by W is equal to M multiplied by G. Knowing the value of M to be given by 0.5 and knowing the value of G to given by 10, so the weight is given by 5. Since everything is in the SI, so the value of W will be expressed in the SI, which is in newtons. The magnitude of the weight is given by 5 in newtons. Now in 1.2, indicate that the direction and the line of action of W. So we always know that the weight acts vertically downwards. So the line of action is vertical and the direction is downward. So this is the sphere S totally immersed in the liquid, so the weight will be acting on this point vertically downward like this. Now part 2 of this exercise, apparent weight of S. The sphere S is totally immersed in water, as shown in the adjacent document. So they mentioned this document, now we can use it. In part 2.1, calculate the magnitude of F of Archimedes upthrust F exerted by water on S. So let's discuss the different ways that one can calculate the magnitude of F. So let's suppose that F can be calculated using the real weight minus the apparent weight. However, in this case, we don't know the value of the apparent weight, so we cannot use this equation. So the other method is given by the condition of equilibrium. Okay, so let's discuss the condition of equilibrium. So as a title, we write at equilibrium. So on the left hand side, we write the different forces acting on S, and they are given by, so let me make it here clear. So they are given by the weight vector of upthrust, but they aren't the only two forces acting on the solid S here, because we have a support, which is the bottom of the container in contact with the solid S. So in addition to these forces, we have the other force, which is given by the reaction, so plus R vector is equal to 0 vector. Then we cannot use this condition in order to determine the magnitude of F, since we know W. However, if W and F are the only two forces acting on the solid S. So this is given by zero vector. Then dragging F to the right hand side, we will have that W vector is equal to minus F vector. And by this equation, it means that they both have the same line of action, opposite direction, same magnitude. So in this case, we can deduce that the magnitude of F is the same of W, which is 5 Newton. But this is not the case here because we have an additional force which is given by the reaction. Okay, so we cannot use this method. So we are only left with the formula of F, which is given by that F upthrust, which is denoted by F, is equal to the density of the liquid, which is denoted by rho, multiplied by the volume. So let's say like this, multiplied by the volume of the immersed part multiplied by G. Here, because S is totally immersed, then we have that VI is equal to V. Now let's say since S is completely immersed in the liquid, which is given by water, then VI is equal to V. Recall that they usually give a half a mark for this statement, so this statement is important. Now let's rewrite the expression of F replacing VI by V. So the magnitude of F, which is denoted by F upthrust, which is denoted by F, is equal to the density of the liquid, which is denoted by rho, times the volume of the immersed part, which is equal to the total volume, multiplied by G. No need to construct a triangle for this formula because this is the quantity that we want to calculate. Now the value of rho is given by 1000 and the value of V is given by 2 times 10 to the power minus 4 and the value of G is given by 10. Now plugging this on the calculator, then the value of F is given by 2. Since everything is expressed in the SI, so the value of F will be expressed in the SI, which is in newtons. So the value of the force exerted by the liquid on the solid S, named to be the Archimedes upthrust, is given by 2 newtons. So here let me write that the magnitude of F is given by 2 newtons. Now 2.2 indicate the line of action and the direction of F. So let's say that the line of action, we know that always F upthrust opposes the action of the weight, so the line of action is vertical. However, the direction is upward. Now in 2.3, deduce the magnitude of W apparent, and by deduce it means that we need to use the previous parts. So in part 2.1 we have determined the magnitude of F, and we know that referring to the definition of F is given by the value of the real weight, which is denoted by W, minus the value of the apparent weight, and we are interested in determining the value of the apparent weight. Now replacing the values here, the value of F is given by 2, the value of W is given by 5. And we keep W apparent as a variable. So what's the type of this equation? This is a linear equation in one unknown. The unknown is given by W apparent. So how do we solve this equation? We put W apparent on one side and all the other numbers on the other side. Now dragging W apparent to the left hand side, and it will gain a minus sign. Minus with minus, it will give us plus. So it's given by W apparent. Now keeping 5 in its place, dragging 2 to the right hand side, so it will gain a minus 2 from plus 2 to minus 2. Now the value of W apparent is given by 3. Since both 5 and 2 are expressed in newtons, so the value of W apparent will be expressed in newtons. So W apparent is given by 3 newtons. Now part 3 of this exercise and the final part. Force exerted by the bottom on S. So here we are referring to the opening of this exercise or the aim. Now the sphere exerts on the bottom of the container a force R1 of magnitude R1 is equal to 3 newtons. So here they are telling me that what does R1 represent? It's the force exerted by the sphere on the bottom of the container. So because the sphere rests on this container, now let's forget for this moment the forces. So here we have many forces acting on the sphere. So in particular the weight, F upthrust, the reaction at the support. Okay, so let's forget about these forces and consider the forces mentioned in this part here, because we are discussing the principle of interaction. So what does R1 represent? It represents the force exerted by the sphere They are telling me the sphere exerts, so the force exerted by the sphere on the bottom of the container. So this is the force R1, let me represent it here, exerted by the sphere on the bottom of the container. They are telling me that the magnitude of R1 is given by R1 is equal to 3 newtons. Determine using the principle of interaction the magnitude of the force R2 exerted by the bottom of the container on S. So here let's say that the solid S and the bottom of the container are being at interaction. So as the sphere exerts a force R1 on the bottom of the container, so according to the principle of interaction, also the table will exert a force on the solid S, which is given by R2. Then let's represent R2. So this is R2. Both of them having the point of application, point of contact between the interaction of the two bodies. So they are telling me using the principle of interaction. So let's write as a title, according to the principle of interaction. Then how do we apply this principle? Always on the left we write one of the forces. So let's suppose that this the force that we want to write on the left is given by R1, and on the other side of this equation we will write the other force given by R2, and we don't forget the minus sign. So this is very similar to the second equation for the condition of equilibrium. Now what does this equation means? It means that both forces have the same line of action, opposite direction, and same magnitude. Since the magnitude of R1 is given and we are interested in determining the magnitude of the force R2, so let's say in magnitude we have that the value of R1 is equal to the value of R2, but we know that the value of R1 is given by 3 newtons. Then in this case the value of R2, the magnitude of the force exerted by the bottom of the container on S, is given by 3 newtons. So R2 is equal to 3 newtons. So now, okay, so this is it for this exercise, but let me say the following. So we have determined the value of F, and the value of F is given by 2 newtons from here. And the value of W is given by 5 newtons. So knowing that the weight acts vertically downward and F acts vertically upward, so why the solid S is at equilibrium? So there must be another force opposing, so helping the force F in order to oppose the effect of the weight, which is given by 5 newtons, and this is given by the magnitude of R2, which is given by 3 newtons. So in this case, because F and R2 act vertically upward, both of them having the same line of action, both of them having the same direction, so 2 plus 3 is equal to 5. So in this case, the effect of both forces F and R2 balance the effect of the weight W. And now let's move to the final exercise for this part, which is exercise number 17. The aim of this exercise is to determine the density ρ L of a liquid L. For this purpose, we consider a solid S of mass m and several liquids of different densities. So here, let's say that the liquid is of density ρ L, and the solid S is given by a mass m. Okay, number 1. S floats on the surface of one of these liquids of density ρ. So here, because S floats on the surface of the liquid, so at any moment, and in this exercise we can use the condition of equilibrium, and the density of this liquid in this case when S floats is not denoted by ρ L, however it's denoted by the density ρ. Now in 1.1, give the name of each of the two forces acting on S. Now because the solid S has a mass, then it will be directly subjected to the weight W vector. And because we have a liquid, then it will be directly subjected to the Archimedes upthrust. F upthrust. Now in the same part, they are telling me to indicate for each of these two forces whether it's a contact force or force acting at a distance. We know that the only three forces acting at a distance, they are given by the weight, the electric, the magnetic. So the weight W is classified as force acting at a distance, and all other forces are classified as contact forces, and in particular F upthrust. So this is a contact force. We are in the same part 1.1. Now in 1.2, write the condition of equilibrium of S, knowing that it floats on the surface of one of these liquids denoted of density rho. So indeed we can use the condition of equilibrium. Then how do you apply this condition? Always as a title we write at equilibrium. Then on the left we write the sum of forces acting on the solid S, and they are given by the weight F upthrust. And on the other side of this equation we write the zero vector for corresponding for the condition of equilibrium, and we don't forget the vector over 0 as well as W and F upthrust. Now moving F upthrust to the right hand side, we have that W vector is equal to minus F upthrust. What does each of the equation tells us? So the first equation tells us that the effect of both forces acting on the solid S cancel each other, whereas the second equation tells us that both forces have the same line of action, opposite direction for the minus sign, and same magnitude. Now in 1.3, deduce the expression of M in terms of rho and the immersed volume Vi of S. And by deduce it means that we need to use the previous part. In 1.2 we have determined the expression of the condition of equilibrium, and in 1.3 we need to deduce the expression of M in terms of rho and the immersed volume Vi. So what does this mean? So we need to determine M, so putting M on the left hand side, so it must be equal to the combination between the density rho and Vi. So for example, one of the possible answers as an expression may be like density divided by Vi or density multiplied by Vi. So we need to determine such an expression, but referring to the condition of equilibrium. So the condition of equilibrium is given by W is equal to minus F upthrust. Now here, because M appears in the real weight, which is given by M multiplied by G, which means that we are interested in the magnitude. And here let me clarify also the following, that what does this weight represent since we have a liquid? Does it represent the real weight or the apparent weight? For sure, because we are discussing forces, we are interested in the real weight and not the apparent weight. So, and we are interested in the magnitude. So let's say in magnitude. Now dropping down the vectors and removing the minus sign, we have W is equal to F upthrust. But knowing that the value of W is given by M multiplied by G, and the value of F upthrust is given by the density of the liquid times the volume of the immersed part times G. Because we need to deduce the expression in terms of M, rho, and Vi, so we must replace W by M and F upthrust by rho L times Vi times G. Now this is the equal here, replacing W by M multiplied by G. So this is the equal, we have M multiplied by G. And on the right hand side, replacing F upthrust by rho L times Vi times G. Now the density of this liquid in this case is denoted by rho, and the volume of the immersed part, okay, it's denoted by Vi multiplied by G. Let me write here that M multiplied by G. Now this equation is independent of the value of G because we can simplify G on both sides. Then the expression of M in terms of rho multiplied by Vi, in terms of rho and Vi, is given by that M is equal to rho times Vi. So this is the expression that we want. And let me write here that M is equal to rho multiplied by Vi. So indeed we have M on one side, and it's a combination between rho and Vi. Now in number 2, as the liquid is changed, why? Because they are telling me we consider a solid S of mass m and several liquids of different densities. So as the liquid is changed, the density ρ varies and the immersed volume Vi of S varies too. We draw the graph of Vi as a function of 1 over ρ curve below. So let's consider this graph. First of all, what's the shape of this curve? It's a straight line. Does it pass through the origin? Yes. Although here, okay, we can prolongate this line. So as we prolongate it using the ruler, we can see that this line passes through the origin. Now the y-axis is labeled by the quantity Vi, which represents the immersed volume. It's expressed in centimeter cube, so centimeter cube is not the SI unit of volume. The y-axis is labeled by a non-trivial quantity, which is given by 1 over ρ, and its density is given by centimeter cube per gram. Why? So knowing that one of the units of the densities is given by gram per centimeter cube. Now, but notice here the x-axis is not labeled by ρ, it's labeled by 1 over ρ. So it's the reciprocal of ρ and not ρ itself. So here, in this case, if we do the reciprocal of gram per centimeter cube, so what do I mean by the reciprocal? So the numerator will be the denominator, and the denominator in this case will be the numerator. For this reason, the density of 1 over ρ is given by centimeter cube per gram. Okay, so 2.1, show that the slope of the obtained curve represents the mass of S. Now, we need to, in other words, we need to determine the slope. Now, we know that the equation of a line is given by y is equal to ax plus b. Okay. So in this case, the value of b is given to be 0. Why? Because it's a straight line passing through the origin. So the equation of this line is given by y is equal to ax. So this is the y, this is the x. What does a represent? A is the slope. So so if we construct a triangle for this formula, which is given by y is equal to ax. So here, because we have a multiplied by x, so y will be at the top, a and x here. We are interested in determining the value of a, so a is given by y divided by x. So the value of a, the slope, is given by y divided by x. So a is equal to y divided by x. What does y represent? Y represents the volume of the immersed part. And what does x represent? It represents the density 1 over ρ. So in this case, we need to calculate the slope. So let's say that the slope is equal to the volume of the immersed part, which represents y, and 1 over ρ, which represents x. Now here, because Vi is not divided by anything, so we consider it to be divided by 1. Now here, Vi multiplied by ρ and 1 multiplied by 1. So in other words, far with far, near with near. So it is Vi multiplied by ρ divided by 1 multiplied by 1. But knowing that in part 1.3, so it is Vi multiplied by ρ. But knowing that in part 1.3 we have verified or deduced that the mass is given by density times Vi. So what does ρ times Vi represent? It represents the mass, which is equal to m. So let's say then the slope represents the mass. So just a side remark, since here we are calculating a slope, why I didn't use the method which is given by, for example, like that we have used in resistors, which is given by in the chapter of resistors, which is given by that R is equal to the voltage of the point A minus the voltage of the point B divided by IA minus IB, because previously we were using this method in order to calculate a numerical value of R. For example, we used to calculate that R is equal to 200 ohms using this method. Now I'm using this method not to calculate the value of m, but in order to verify that the slope is equal to the mass. Okay? Now in 2.2, in the case of the liquid is Vi is equal to 100 centimeter cube, determine the density rho L of L. So in other words, we need to use the graph in order to determine the density rho L of L. So let's say graphically. Usually they give a half a mark for this statement. Knowing that, in order to determine the density, we can refer to this graph. Why? Knowing the volume Vi, which is given by 100 centimeter cube, we can refer to this graph to determine the value of, not rho, but 1 over rho. But knowing the value of 1 over rho and the cross multiply, we can determine the value of rho. So let's say for Vi is equal to 100 centimeter cube, which is given by this value corresponding to this point of the curve, having a value of 1 over rho is given by 0.5. We have 1 over rho is equal to 0.5. What's the unit of 1 over rho is given by centimeter cube per gram. So 1 over rho is equal to 0.5 centimeter cube per gram. But knowing that we are interested in determining the value of, so here the density in this case is denoted by rho L. So 1 over rho L is equal to 0.5 centimeter cube per gram. So let's not write the unit. We are interested in determining the value of rho and not rho L. So how to determine rho L from this equation? This is an equation and one unknown rho L. How do you solve this equation? We put rho L on one side and all the other numbers on the other side. So here 0.5 is not divided by anything, so it's divided by 1. Now if we cross multiply, we have that 1 divided by 0.5 is equal to rho L. Then the value of rho L is given by 2. Now what's the unit of rho L? Because 1 over rho is expressed in centimeter cube per gram, then its reciprocal, which is given by rho, is expressed in a gram per centimeter cube. So the unit of rho L in this case is given by gram per centimeter cube. Knowing that a gram per centimeter cube is not the SI unit of density, in order to convert from a gram per centimeter cube to kilogram per meter cube, we multiply by 1000. Then 2 multiplied by 1000, then the density of this liquid is given by 2000 kilogram per meter cube. So the density rho L is given by 2000 kilogram per meter cube. And that's it for me in this video, guys. See you soon in a new one.